In this video we're going to look at how we can use 2x2 matrices to obtain transformations of two-dimensional space. Just a little bit of notation to begin with. If we've got the triangle with vertices 1, 1, the point A, the point B is 3, 1, and the point C is 3, 2, then the position vector of A is the vector joining O to A, which is the vector 1 in the x direction, 1 in the y direction. Similarly, the position vector of B is the vector 3, 1, and the position vector of C is the vector 3, 2. Now we can use matrices to define transformations in the following way. If we want to find the image of the point 1, 1 under the matrix 2, 1, 2, 2, then we take the matrix and we multiply it by the position vector of A to obtain the position vector of the image point, which we'll call A dash. So to obtain A dash, we take the matrix and multiply it by the position vector. 2 times 1 plus 1 times 1 gives me 3, and 2 times 1 plus 2 times 1 gives me 4. So the point A dash is the point 3, 4. Similarly for B and for C. So B was the point 3, 1. So to find the image of B, we need to multiply the matrix 2, 1, 2, 2 by 3, 1. So that gives me 2 times 3 plus 1 times 1, which is 7 as the top entry, and 2 times 3 plus 2 times 1, which is 8 for the bottom entry. So the point B dash is the point 7, 8. And for C, we need to take the matrix 3, 1, 2, 2 and multiply it by the position vector of C, which was the point 3, 2. So we've got 2 times 3 is 6, plus 1 times 2 is 8, and 2 times 3 plus 2 times 2 is 10. So the image of C is the point C dash with coordinates 8, 10. Now we can now show the original triangle and the image triangle in a diagram, and we can see that this matrix 2, 1, 2, 2 has quite an odd effect to the triangle ABC. It's stretched it and it's also rotated it a little bit. Now we can save the amount of work in calculating the points A dash, B dash and C dash by writing the calculation as a single matrix multiplication. So we've got the matrix 2, 1, 2, 2, and then we combine the 3 points into a single matrix and do the matrix multiplication in the normal way to obtain the image points, which then again gives us exactly the same diagram as before. Now let's have a consider the effect of the matrix 0, 2, 2, 0 on the triangle ABC. So we need to multiply the matrix 0, 2, 2, 0 by the coordinate matrix, where A is 1, 1, B is 3, 1, and C is 3, 2. So if we do that multiplication, then we obtain 2, 2 as the image of A, 2, 6 as the image of B, and 4, 6 as the image of C. Check that matrix multiplication that you're happy with that. So we can draw the diagram showing the triangle ABC and its image A dash, B dash, C dash. And we see that the image triangle is twice as large as the object triangle, but there's also been a reflection in the process. If we just throw in to the diagram the enlargement of the object triangle by scale factor 2, then we get the dotted triangle. And to move the dotted triangle onto the final image triangle, we need to do a reflection in the line y equals x. So we can say that the matrix 0, 2, 2, 0 has the same effect as an enlargement of scale factor 2 and centre the origin, followed by a reflection in the line y equals x. Now the next question says, under the transformation with matrix M, which has the matrix M, which is 3, 5, 1, 3, the image of the point P is the point 4, minus 8. And we have to find the coordinates of the starting point, the object point P. So let's suppose that P is the point HK. Then what we're being told is that the matrix times by HK must equal 4 minus 8. So we've got 3H plus 5K must equal 4, and H plus 3K must equal minus 8. So we've got a pair of simultaneous equations. Solving these equations using normal methods, or indeed by using your calculator, we obtain H equals 13 and K equals minus 7. So the point P is the point 13 minus 7. Now at this stage, I'd like you to pause the video and have a look at the questions on this sheet here. When you've had a look at these questions, carry on with the video. Of course, there's a little bit more that we've got to have a look at before we finish. Okay, then. We're going to have a look at the transformation given by the matrix cos theta minus sine theta, cos theta. Now when theta equals 0, we've just got the matrix 1, 0, 0, 1. That's the identity matrix. So when we multiply the coordinates of u, v and w by 1, 0, 0, 1, we're simply going to get the same coordinates coming out again. So the image triangle is identically the same as the object triangle. However, as soon as we increase theta, so let's take theta up to 10 degrees like that, we can see that there is a difference between the object triangle UVW and the image triangle U-V-W'. And let's now let the value of theta increase slowly. And you can see that what's happening is that the triangle is turning around the origin, and that at any stage the angle that it's turned through is exactly the same as the value of theta. So let's just have a look at that once more, send it back, and then we'll send it on its way. So we can see the triangle is turning around the origin, and at each stage the angle through which it has turned is exactly the same as the angle theta. So the matrix cos theta minus sine theta, cos theta represents a rotation of theta anticlockwise about the origin. So we've seen that GeoGebra gives us a typical output looking something like this, that when theta equals 110 degrees, the triangle UVW has been rotated round by 110 degrees anticlockwise about the origin. So we're saying that the matrix cos theta minus sine theta cos theta gives us an anti-clockwise rotation of theta about the origin. Now there's a second matrix that we're going to investigate, and this is the matrix cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta. And again we're going to investigate it with the aid of GeoGebra. Now when theta equals 0, the matrix is 1, 0, 0, minus 1. And we can see that the image matrix, the image triangle rather, U dash, V dash, W dash, is simply a reflection of the original triangle, UVW, reflected in the x-axis. If we move theta on a little bit, let's say until we've got 40 degrees, then in this case we can see that UVW is again being reflected in a mirror line to obtain U dash, V dash, W dash, and the mirror line is in fact making an angle of 40 degrees with the x direction. So let's now look at what happens if we allow theta to increase slowly from 0 towards 180 degrees. So in each case we can see that the image triangle is a reflection in the mirror line shown, and that the mirror line makes the same angle with the x-axis, positive x-axis, as the value of theta. So we are saying that the matrix cos 2 theta, sine 2 theta, sine 2 theta minus cos 2 theta gives us a reflection in the line that makes an angle theta with the x direction. So what's the equation of this mirror line? Well, we know that the mirror line makes an angle theta with the x direction. And if we mark a point xy, which lies on the mirror line, then we set up a right angle triangle using the point 0, 0 and the point xy. And we've got the y step is y, the x step is x, so we can certainly say that y divided by x is the gradient of the mirror line. But if we think of it in terms of trigonometry, we've got y divided by x is the opposite divided by the adjacent, so that's going to be tan theta. So the equation of the mirror line must be y equals x tan theta. So, putting all of this together, GeoGebra has shown us that the matrix cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta gives us a reflection in the line passing through the origin, which makes an angle theta with the x-axis. And our little bit of coordinate geometry on the previous slide has told us that this mirror line has got an equation of y equals x tan theta. Now at this stage it's probably worth our while just recapping on what we've already done. We've found out that the matrix K0, 0K gives us an enlargement of scale factor K with centre of enlargement 0, 0. In the exercise we saw that the matrix K001 gives us a stretch of factor K in the x direction with centre of stretch 0, 0. and that the matrix 1, 0, 0, k gives a stretch of factor k in the y direction with centre of stretch 0, 0. We've seen that the matrix cos theta minus sine theta cos theta gives an anti-clockwise rotation of theta with centre of rotation 0, 0. And with special cases of that are if theta equals 90, we've got 0 minus 1, 1, 0 gives a 90 degree anti-clockwise rotation. If theta equals 180, we've got minus 1, 0, 0 minus 1 gives us a 180 degree rotation. And if we put theta equals 270 in, we get 0, 1 minus 1, 0 gives an anti-clockwise rotation of 270 degrees, or equivalently a 90 degree clockwise rotation. And finally, we saw that the matrix cos 2 theta sine 2 theta minus cos 2 theta gives us a reflection in the line y equals x tan theta. And if we substitute in theta equals 0, that gives me a reflection in the x-axis as being 1, 0, 0, minus 1. If I substitute in theta equals 90, then I get the matrix minus 1, 0, 0, 1, giving me a reflection in the y-axis. And if I substitute in theta equals 45, that will give me a reflection in the line y equals x being 0, 1, 1, 0. So we've looked now at how we can use matrices to give us transformations of two-dimensional space. And we'll be looking at some further properties of matrices and transformations in the next video.